So in the rest of today's lecture, we will introduce the concept of Gaussian processes. So the key idea is that this is a Bayesian approach, the popular Bayesian approach to machine learning, which we have not discussed much, but I just wanted to introduce it in the light of some recent developments in neural networks and so on. Suppose we consider a regression problem. So imagine that we have some one-dimensional function and the ground truth might be some observations like this. Now what we want to do is we want to be able to provide some confidence level for each. If we get a new query point, we want to provide a prediction of what y is as well as some confidence levels. So we could say that perhaps our confidence levels might look like this. So the idea here is that for each x that I get, my model will say that the ground truth lies between these two intervals. So this is a confidence interval. Naturally, at the samples, my confidence level interval should be 0 because I know the ground truth, but outside of that, I get some non-zero confidence intervals. And the idea here is that my distribution might look like this. If this is the query point, my distribution would be a Gaussian that might look like this. So it has high density somewhere in the middle and it tapers off as we go away from the true value. So the Gaussian process basically assigns a Gaussian PDF for each value of x. This will be clear once we do a more concrete example. So let's do the example of Bayesian linear regression. So suppose the ground truth function f of x is of the form w transpose times phi of x, where phi denotes some nonlinear transformation. Here w is unknown that we want to estimate, and the labels that we get will be of the form fx plus some noise, where epsilon is Gaussian with zero mean and variance sigma square. Now in our approach, what we do is just assume some prior distribution on W. So we assume P of W is Gaussian, say with zero mean and some covariance sigma. And the likelihood function is known in this model. P of Y given X and W. This will be Gaussian with mean of f of x and and variance sigma square. Similarly, if we have data which is of the form x1, y1 up to xn, yn, and if we denote the data matrix X to be the collection of the vectors x1 to xn, the label matrix as y1 to yn, then P of the vector y given the data matrix X and the weight W will be Gaussian, whose mean will be f of x1 up to f of xn, and variance is sigma square I. This can be written as the Gaussian. Remember, f of x is W transpose phi of x, so we can write this as phi of x1 to phi of xn. We think of phi as sort of the row vectors here times W and sigma square I. Okay. Now what we have to do is we have to compute the posterior P of W given X and Y. So we have to compute the posterior of the weight vector given the data. And for that we use the Bayes rule. So we can do this. We have P of W divided by P of Y given X. So what we are doing is we are actually computing the inference problem. We are computing the posterior of the weight vector given our data. The good news is that this is also Gaussian. This is Gaussian with some mean mu and some covariance matrix A inverse, where these quantities can be computed in closed form. So because things are all multivariate Gaussian, you can plug things in, and what you can show after a bit of algebra is that mu is 1 by sigma square A inverse times some matrix phi times y, and A, the matrix A is 1 by sigma square times the matrix phi transpose plus sigma inverse. And you can see a standard reference. For example, the textbook by Bishop for these calculations. I should mention that phi here actually is the row-wise version of the phi matrix, or is the columns of phi are the different data points. Here I had, it's not this phi, it's the transpose of this matrix. Phi is the transpose of this matrix. So you arrange the values in the column across different samples. So the key point is that when we compute P of W given X and Y, we do not commit to one value of W. Instead, our posterior assigns a weight to each W. We can also continue this and compute the prediction. Now, given an X hat, we want to predict Y hat, the label. Then again we'll compute P of Y hat given X hat and the data and the labels. So this will be the integral of P of Y hat given X hat, X, Y and W, P of W given X, Y, dW. So this is a Gaussian. Look at this quantity, it just depends on Y hat given X hat and W, and this is a Gaussian as well. So you can work with the integrals. This is a Gaussian with some mean mu and covariance A inverse that we saw before. This is a Gaussian whose mean is W transpose phi of X hat and variance is sigma square. And so when you integrate out these two, you will also get a Gaussian. So the product of these two will be a Gaussian with some mean and variance. And you can compute these things in closed form. Alpha is just going to be phi transpose X hat times the mean of the weight vector W, and beta is sigma square plus phi of X hat transpose A inverse phi of X hat. So you can compute these quantities and the model will make predictions for each X. The model will make predictions in this form and you can generate the confidence intervals. So all of this seems like a simple exercise in Bayesian linear regression, but it has interesting connections to Gaussian processes. So now let's discuss the Gaussian process view of this example. So we can think of this function as a Gaussian process. What that means is that the function f is Gaussian, there is some mean and there is some covariance function. So this is the function of interest. This is the mean function and this is the covariance function. M of x is just the expected value of f of x, and k of x and x prime is the expected value of f of x minus m of x times f of x prime minus m of x prime. And this is called the kernel covariance function. So the idea is that the function f of x is a Gaussian process. At each point we have it results in a Gaussian PDF for x. So the label is going to be a sample from a Gaussian distribution with mean m. And if you have two samples, x1 and x2, then they represent a jointly Gaussian distribution, a jointly Gaussian density function, and so on. So what we do in this approach is we assume a prior over the function f. So we assume that the density of f is a Gaussian with mean m and covariance k. We assume a likelihood function p of y given x and the function f is Gaussian with mean fx and variance sigma square. The posterior of f given our data set, so the data vector and the observation vector, given the data matrix and the observation vector, p of f given x and y is a Gaussian with again some mean and some covariance function, where f bar is obtained by k, can be easily computed again using properties of the Gaussians, and k prime is k. This is the data matrix, so it's evaluated row wise. Should write it more carefully. So this is the original kernel minus k evaluated the data matrix, k plus sigma square I inverse and k of x and dot. So this is how we can evaluate the updates and the predictions p of y star given x star, x and y. This will be a Gaussian with f bar at x star and the kernel k prime at x star, x star. So an interesting application of Gaussian process in recent time is infinite width neural networks. So a neural network with one hidden layer is defined as follows. We take, say, x in some d-dimensional space, and our output y is a real number. So the way it works is we have like x1, x2, and so on up to xd. It feeds into some hidden layers. So z1, z2, up to zj. And then there is a bipartite graph between each pair of, no, so I'm not drawing all the connections obviously, but then there is a weight on each pair. So between, so this will be W11, W12, and so on. And then the outputs here will again, we apply some nonlinear activation function at each hidden layer, and we have another sequence of weights, and we sum them up. So here Zj is some function phi applied to the weighted sum of inputs. This is Zj. And we can write it in vector form as Wj transpose x, where Wj is the jth vector. We'll assume that the vectors Wj are sample IID from some generic distribution Pw as initialization. Now the output y will be the weighted sum of the output of the hidden layer, so Vj, Zj, plus some initialization term. So here Vj's are the weights in on these edges connecting the hidden layers to the output. V0 is some bias term. We'll assume V0 is Gaussian with variance sigma square, and Vj's are Gaussians with zero mean and variance alpha over j. And we are interested in the case when j becomes very large. So our output y, which is f of x, can be written as summation of j going from 1 to j, alpha j, phi of wj transpose x plus v0. And this turns out, this is a random process for any given x. Since the alpha j, this should not be alpha j, this should be vj. Since the variables vj and wj are random. Now let's look at the mean of f of x. You can easily see that because the v's are zero mean, this is going to be, the expected value is 0. Now let's look at the kernel function or the covariance function between x and x prime. So this is the expected value of f of x prime. This is the expected summation of j going from 1 to j, vj phi of wj transpose x plus v0, and the summation of I going from 1 to j, vi wi transpose x plus v0. This is what we have to compute, and it's a standard and a simplification. This will become sigma square plus the expected value of the summation of j going from 1 to j, vj square phi of wj transpose x and phi of wj transpose x prime. And all the cross terms will basically vanish. Now the variance of vj square is alpha over j, so we can write it as summation of alpha over j, expected value of summation of j going from 1 to j, wj transpose x, phi of wj transpose x prime. So this is the covariance matrix, the covariance function kxx prime. Now the key observation is that as j becomes large, and because the wj's are chosen IID according to PW, the sequence phi of wj transpose x, phi of wj transpose x prime is an IID sequence. And so we can approximate the kernel function as j goes to infinity as sigma square plus alpha times the integral of phi of wx, phi of wx prime, pw dw. And f of x tends to be a Gaussian process with zero mean and the covariance function k of x, x prime. However, there is an issue here. This is the prior, if you like, on f of x. After we initialize the weights, the function f of x becomes a Gaussian process. In recent years, there is a new line of work in deep learning. It's called the neural tangent kernel, which says that even after training the neural network using, say, stochastic gradient descent, f is also a Gaussian process. So the posterior induced on f after this particular training, which involves which involves stochastic gradient descent, is also a Gaussian process. And this makes the analysis of neural networks tractable. So we won't be covering this in detail, but if someone wants to do a project on this topic, it will be very interesting to do. So this concludes the lecture, and this is the last lecture of the course. So thank you very much.